Hey folks, my name is Tim Sweeney, and I'm one of the lead developers for Weights and Biases Weave application, which is all about sort of facilitating the development and application of LLM technology. Um, I came across this post recently by Matt Schumer. I was just happened to be on Twitter scrolling through. I have no affiliation, where he has posted some code around and a technique around using a heavier weight model to produce the system prompt and a few examples for a lighter weight model, with the effective result being a cheaper model that ideally performs better than the lower cost model would without such prompting. And I think what he's doing is really cool and interesting. And moreover, I thought if he was using Weave, there actually might be some additional value that he's able to get out of the system and able to share with his followers. And also thought this would be a good example to highlight some of the features using a real life use case. So let's go ahead and dive in here. So I'm going to open up his code and open this up in Colab. So what this notebook does, let's make this a bit bigger. What this notebook does is sets up a few different functions that, again, allows the user to specify a large model to help make instructions for a small model. And all I'm going to do here is change a little bit of the structure around just so I can use my OpenAI API keys rather than Octo AI, and just run his code through and through so that we sort of see it working. And then we'll kind of dive into how we might be able to help that user experience. So first off, we want to install OpenAI. We also want to install Weave. So rather than using Octa API, I'm going to use OpenAI. And this package here, setenv collab kaggle.env is sort of a universal environment variable manager. So whether or not you're running the code in the notebook or on your machine, you have a universal way of fetching a environment variable. And then with Colab, you actually have secrets stored off to the side. So this is, for me, I can use these secrets and without sort of hard coding them into the notebook. So it looks like the installation is correct or complete. Let's go ahead and grant access so that I have that environment variable. So that's really the first change. Now let's kind of scan through Matt's code. First off, I'm going to comment out the Okta-specific stuff that's going on here, or Octo AI-specific stuff, just to use the out-of-the-box OpenAI. And then he defines a small model here and a large model here. I'm going to go ahead and instead of using Meta, I'm going to use, let's see, GPT 3.5 Turbo probably for the small model, and then GPT 4.0, oops, come on, GPT 4.0. Okay, cool. I think that's the only changes I need. So basically he has a method here that takes in candidate prompts, or excuse me, it generates a set of example input and outputs from the large model to be used in the small model. There's another function, generate system prompt, which uses the large model to write a system prompt for the small model. There's a test small model function, which basically stitches those things together and then calls the new small model. And then a run conversion process, which is just sort of some infrastructure around this method to sort of take in the user input and run through these operations. So let's go ahead and run this, and then we have an example task here. So the task is refactoring complex code. We have a prompt example that contains some code that calculates a price total, but sort of has some funky switch statements going on here. And then we have a response example, which is a more sort of cleaned up version of the same code. Again, this is all part of Matt's code. All I did was change the OpenAI connection strings. And then we'll go ahead and run the process here. Now, my testing earlier basically takes about 30 to 40 seconds per run, and so I will snip this out of the video or fast forward from here. So great, it looks like the process ran successfully, and we have an output with some revised Python. So that's great. Now, the way that Matt has set up his code is that it will write to a local file, smallprompt.py, that contains the system prompt and the messages. And this is great. However, I think that this could be improved. So let's say that I want to share this prompt or I want to share this collab with folks. They need to kind of know how to read that prompt. They need to know what to do with it, maybe how to get it out of Colab. Shareability is a little bit challenging there. And moreover, as I'm exploring sort of different examples and different inputs as I'm iterating and exploring here, I'm going to lose that history, right? As soon as I run something else here, this cell is going to go away and the insight might be locked in my mind, but beyond that, I have no record keeping. So these are some of the fundamental problems that we've sort of seeks to solve for LLM application developers. So what we're going to do here is just annotate our code very, very subtly. So let's import Weave. And let's see here. All I'm going to do is a few things. I'm going to add @weave.op to the handful of functions that sort of make up the core composition of this application. So I'm going to add op to generate candidate prompts. I'm going to add op to generate system prompt. I'm going to add op to test small model and also run conversion process. What @weave.op does is it says, please track the inputs and outputs and a bunch of other like system metrics and performance metrics about the execution of this particular operation. And we'll track it and have it available for you to review over time. We also capture code and a bunch of other data associated with the execution of that particular function. So we'll go ahead and run this again. And then right before we actually call the top level method here, let's do weave.init. This says initialize a project. If you don't do this, those other annotations are no ops. So I'm going to Tim S. Sweeney. So this is my entity within Weights and Biases. And now let's do sort of, this is a large to small model example. Sure, let's call it that. That's the project name. This is where all that data assets will be stored. So let's go ahead and run this. I don't think I'm logged into Weights and Biases right now. So in the case that I'm not logged in, it'll give me a small prompt to log in. So I'm going to click this authorize link and paste it in. Now the local collab session has been authenticated with Weights and Biases, and the Weave library has been instructed to write its logs to this particular project. Great, and it's complete. So as you can see, we get the same output as before, except we now have a link to the trace that was captured with Weave. So let's go ahead and click in. So what you're seeing here is the captured trace for the code that Matt wrote. We see that we have this run conversion process as a top-level method that was executed. We can see the user inputs that were, or the inputs to the function that were provided, as well as the output dictionary that was tracked. This is essentially what is being stored to disk in the current Colab implementation. However, now this is tracked forever, and we can always go back and restore this information. We can even see all of the generated examples. So here's one example of such. Next, we can see on the tree of calls. So the first sub-procedure or sub-method that was executed was generate candidate prompts. We can see that that cost about 5 cents, and it used GPT-4o mini. Here's the breakdown of the cost. We can see that that then called out to OpenAI. So I can click in and see the specific inputs and outputs for this procedure, as well as the actual OpenAI calls that were sent to, or the request and response to OpenAI directly, or whatever vendor of choice you might be using. Weave supports, I think, about 12 vendors out of the box, and more are being added every day. We can then see that after generating the candidate prompts, we generated a system prompt, which followed a similar tree structure, and then we tested the final model. And we can see, again, the costs across. So here we see that most of the time was consumed generating the prompts, and that's where most of the cost was, and that the small models test was actually much faster and lower cost. So that does corroborate some of Matt's claims there, which are awesome. Secondly, we can also note that we can take a look at the code. So code is automatically captured with Weave, so we can sort of retrospectively say what code actually ran underneath the hood. As you're probably familiar, as you're working in notebooks and other interactive environments, it can be challenging to track changes that aren't checked into version control. With Weave, this kind of thing is automatically tracked. We can see feedback, which we'll talk about a little bit later, as well as a summary of what the system state was, or the environment, how long it took, who ran the operation, as well as the cost and usage. So yeah, this is kind of the first fundamental value is with a few annotations, you're able to track and record all different sorts of activity and track code, track versions, see the cost, latency breakdowns, etc. If I was continuing to work with this project and creating more and more iterations of different ideas, we would see more and more rows show up here, sort of outlining the different inputs and outputs that the particular operations created. So that's kind of part one here. Now, kind of moving into part two, the next thing that someone might want to do is make these models reusable, so that maybe I can generate one of these models and then sort of save it in a way that can be later retrieved, even in a different collab or maybe via a link that I send a colleague. So what I'm going to do is slightly modify Matt's code and refactor that slightly. So there's a method here, test small model, and inside of test small model, what it actually does is it kind of constructs the model and then calls it. So we can kind of break that into two different sort of responsibilities here. So first, let's create a class. Let's call this class let's call it supercharged mini model, because that's the name I'm thinking of right now. And we are going to call this a weave.model. A weave.model basically tells the system, hey, treat this as a model, and really the only requirements are that you define a predict function, and the UI and organization will sort of give you more affordances because this is now a model. Now, what we're going to do is we're going to define a predict op that takes self, and I'm not quite sure what else it's going to take yet, and it's going to return a string. And let's see here. Let's just copy this exact code into here and see what we need. So it looks like a system prompt should probably be part of the class definition. And generated examples is also part of the class definition. That's a list of dicks. Yeah, it seems like the typing here is more of a suggestion. It doesn't necessarily need to be perfect right now. And then lastly, there is this prompt example. So prompt example is actually the user input. Okay, and this looks right to me. Great, and we are going to say at weave.op on top of this. Now, one small subtlety here. Let's go to where the client is defined. This will come in handy later. When we're using a client in an op that we want to later retrieve, it's useful to do that construction inside of the op itself, and we'll talk about that in a moment. But trust me, this is a nicer way to write this for now. Okay, now with the small test model, let's go ahead and create my model. And my model is going to be equal to my supercharged mini model with a system prompt and some generated examples, and then we're going to return my model.predict that. Great. Okay. So what do we do here? We simply refactored this test small model method in order to construct a instance of a class that contains the sort of static properties about that model that have been learned from the larger model, and then we called predict. So this is a very natural sort of way that the code might look. However, there's a very nice property here, and that's that when we do this sort of creation and then call predict, Weave is actually going to track this object inside of its data model over time, and this can actually be shared and downloaded later with colleagues, friends, etc. So let's go ahead and run this, and then we will run the exact same thing one more time. Okay. And once again, I'm going to sort of pause the video or speed it up while we wait for the response. Got it. Okay, so the procedure is finished. And again, we are familiar with the output by now. Let's go ahead and open up our application one more time. What you'll notice here is it looks nearly identical, except that this test small model now has this nested supercharged mini model.predict call. And we can see that the self object has been tracked. So here we can jump into this model, and we see that we've tracked the predict function, and we have the generated examples. So this view right here is it's our object viewer. It's a saved instance that is now serialized into the Weave system. If we click on models, it is actually stored here. We see we only have a single version at this point in time, and we have all of the associated properties. What we're going to do is get into this use tab where we can see how it was downloaded or how to download it. But before we do that, I want to show something more subtle that we touched on before. So here I've run two conversion processes. The first one doesn't emit the model, the second one does. Now, interestingly, we note that we changed the test model code here, test small model code. And if I look at the code tab for test model, you'll see that we've captured this class definition as well as the modified code itself. What's really great about this is if I go ahead and go to summary and click on the operation itself, I can click diff versions. And what that's going to do is show me the version, what actually changed between those points in time. Again, if you're working in notebooks, this is really valuable. Most of the time, as we're software engineers, we are checking out code, working locally, committing our changes and pushing it up for our colleagues to review. However, with sort of interactive and sort of dynamic systems like this, where you're querying it, getting feedback, sort of building a mental intuition of how your system works, there's a lot of changes and insights that occur that are not captured with the traditional source version control systems. So Weave sort of complements that workflow and allows you to track these changes both to runtime objects, like we just saw with the model tracking, as well as code, so that you can work fluidly within your interactive environment, but also track those changes and have a reproducible system, and later go back and see what was the state of affairs when I had this particular outcome. Okay, great. So now let's go back to our models tab. And I want to sort of, this is, I guess, my call to action to Matt out there is, it might be interesting for you and your users to set up a project where a bunch of people are making models that then can be shared. So let me go ahead and click this use tab, and I'm going to select this, copy this code that says use this code to retrieve the model version. Now I'm going to open up the notebook and go into a new cell below, and I'm going to copy that code. It's a bit long, so I'm going to break it into a couple parts. So we have a URI. Okay, so what are we looking at here? First, we have a URI ref. All objects inside the Weave data model are immutable and uniquely identified by their ref. So here we have a Weave schema, followed by the entity, the W&B entity that I logged to, followed by the W&B project, followed by the sort of object type. This is a little bit meta because it's an object type, but that's what this is. And then we have the name of the object, and then followed by a content digest. So this is a content addressable reference to this particular data payload. This could be something that's shared. If I open up my project and make it public, anyone in the world would be able to download this model. So here I then instantiate the ref. This basically is a more structured pointer to this object. And then I ask the Weave system to fetch that ref and reconstruct it. So let's go ahead and run that code. Great, so now I've gotten the model, and here's where the magic comes in. I can say gotten model.predict, and I can go ahead and pass it. Let's go ahead and pass it that same prompt example from the beginning. Okay, and it's going ahead and executing. And we see the response output here. And so there, I want to emphasize this point, that this code is not running the code that's above in the notebook. This code has been downloaded from Weights and Biases, or Weights and Biases Weave. It's been downloaded and dynamically bound to this object. So you don't need the actual code definition above. Anyway, it's a really nice way to have sort of portable code that encapsulates a definition of a model, in this case, a system prompt and some generated examples, as well as pair that with some code that then constructs the predict, or constructs whatever sort of logic you want. This is not limited to models. You can write any class that sort of conforms to these sort of Weave.object standards and sort of serialize and deserialize them like this and share them with your audience. So yeah, that's how that works. This that I'd like to show is sort of more formalizing this concept of evaluation. So Matt very rightly in his post sort of claims that what the purpose of this procedure is to take a large model that is more expensive, use it to construct a system prompt and sort of the structure for a smaller model, and then achieve greater performance. So some of the things that we might want to measure are does the smaller model actually perform better? So sort of a measure of quality. We also might want to measure latency. Does the smaller model or this procedure run faster than potentially a larger model? We also might want to measure cost per the example, like, we have a 30x less expensive model, and does that correlate with an equivalent quality score, right? And so we want to kind of add some sort of formality to these claims, and not just because it's important to do that externally, but if you're in a business and you're actually trying to apply LLMs, you need to justify that this iteration on your prompt or this iteration on this concept is worth deploying to your end users. And so we sort of represent that concept in this form of an evaluation. So in Weave, there's an evaluation framework that allows you to formally define the sort of unit test, if you will, for a model, and then view those results in the UI. So in this collab, I already wrote the evaluation code. So everything we've shown so far, the at-op and model stuff, are kind of like super lightweight things where Weave says, hey, in a very, very inexpensive way, you can track your work, share your work, version control between commits, identify errors, etc. Now, to do the evaluation, it requires a little bit more thought, and I didn't want to consume the video time sort of writing that code. So I wrote it beforehand, but I'm just going to talk through it. So let's go ahead and scroll all the way down here. Basically, the way that I rationalized this problem was I first said, okay, I'm going to build a build dataset method. And this build dataset is going to build a simple dataset with 3 examples. What does make example do? So make example basically is asking an LLM to generate test cases for this problem case. So essentially, I have some example user input here. The example user input is like some messy input. Then there's some clean code, which is an example of a better formulation of that same logic. And then sort of a editor's comment. and I ask an LLM, I say, you're a computer science 101 professor making a small quiz for your students. Your students are learning about refactoring and clean code. You should emit a JSON payload with user input, clean code, and comment key. The value for user input would be a short 3 to 5 line Python function that works, but has some style, control flow messiness. The value of clean code shall contain more beautiful version of the function. Finally, the value of comment shall contain a short note describing what changed and why. Remember, these are 101 students, so don't overcomplicate things. Think about ternary operators, list comprehensions, and the like. Feel free to be fun and creative with the example functions. So again, we're kind of asking an LLM to build a test set, essentially. I also ask an LLM to be a judge. So here we say, you are a computer science 101 professor making a small quiz for students. Your students are learning about refactoring the code. You'll be presented with a couple things, right? User input, clean code, comment, and then the student's answer. Your job is to grade the student results. You shall carefully consider the user input and clean code and comment as a baseline. Then look at the student code and grade the quality of their answer between 0 and 100. The student code need not exactly match the clean code example. Rather, your goal is to grade the quality of the response. So now we're trying to say, okay, like, hey LLM, can you take these sort of example items and the model's output, and then give sort of like a give a quantitative score to the quality of that result. Cool. So and then we have some sort of additional structure here to do that. Okay, so all this comes down to this, where we call build dataset, and then we have this, we define an evaluation. So we say, let's go ahead and define an evaluation with a data set and that one score. You can have many scores. They can be rule-based, they can be heuristic-based, they can be LM-based. These are purely functions that are called on the inputs and outputs to generate some form of logic. And we can point you to the docs on all the different things that you can do here. Okay, so we run that guy, and then we create a baseline model. So here, this model without logic is simply a model that returns the original user input. I like to have a baseline model like this just to make sure that my system is set up and that like the evaluation framework's working and that we have kind of all of our mechanics in place. I go ahead and run that, and we get a link out to our project. Okay, awesome. So let me open up my project. I'm going to go to the evaluation tab, and we can see I just ran this evaluation on this model without logic. So we can jump in and see we've actually ripped through the 3 examples. I can, if I'd like, I can go through and see the data set of sort of user input, clean code, and comments. Also, if I'd like, I can jump in and see each of the individual predictions and scores. And what's nice about this is I can see the logic. So I can see here the judge took this response, and in this particular case, gave the score of 90 with a reason the student code correctly implements the logic, but can be further improved with a ternary operator, etc. So we can see the internal judge and how it operated as well. Now, here's where it gets a little bit fun. I previously got my gotten model. Let's take out that comment. I previously got my gotten model, and I'm going to run the same evaluation against that gotten model. So now I'm saying, okay, great. I would like to ask the model that I used Matt's framework to build to run against the same evaluation. And we can see that the mean score is higher than the mean score on the prior. Now, this is where we can build a report. So let me go. Oh, awesome. It's right here. Great. Okay, so I have 2 evaluations. I'm going to select both of them and then click compare. So the pink one is the one that actually contains Matt's really smart instruction work, and then the blue one is the baseline. So we can see that the new model performed better on the judge score. It performed took much longer, obviously, because it's calling out to LLMs, and it used far more tokens, obviously. Here we can see a rollout of the scores. We can also see we can see exactly like what differed. So here we can see the predict functions differed. If we want, we can click in and say, okay, here's the dummy predict, and here's the more complicated predict. We can also drill into specific examples. So here I'm going to drill into an example where the baseline model did very poorly and the competitor model did quite well. And if I scroll to the bottom here, we can see that we had some user input. Here's a reverse string example. And we can see that the baseline model obviously just returned the normal, original string, and the new model actually has this really nice reverse function. In fact, our scorer thought that deserved a 95. So we can click in and see what happened here. We can see that the scorer said the student code is concise and correctly implements the reverse score function using slicing. However, they could have added a doc string to explain the purpose of the function. That's fair. Fair enough. So, you know, it's a good score. And why did we get a 70 for this other one? So it says the student's code is identical to the messy code provided, missing the simplification through slicing. However, proper indentations maintained. So a little bit harsh on the smart student and a little bit easy on the baseline, I think. So this is just a great example of how we can use Weave to sort of track some of these concepts, and then actually dive in and make some build some rationale around how we can improve the system. And everything here is linkable. So you can say, how did this particular result happen? I simply click here, and I can see exactly the call that happened out to OpenAI. I can see the code that was used. I can see when it was called. I can see the user input, etc. So yeah, and of course I can clear this selection and page through all of the different examples that occurred. Yeah, so that's kind of how you could use evaluations to further complement this work. And for what it's worth, this is a public URL. Of course, I'm in a locked down project, but if I was to make this project public and save that, then I should be able to copy this, go to a new tab, and oops, well, I suppose I could just log out. That would be probably the best thing to do. Let me log out and go to that URL. So this is something I could share with colleagues to say, hey, take a look at this improvement I made, or if I want to share with my audiences, or I want to let people download these models. So that's it. I think that covers a couple different things. There's a bunch more: error tracking, cost comparison, feedback, building data sets that we didn't cover. Yeah, thanks in advance to Matt. He doesn't know that I'm doing this. Again, we have no affiliation, and hopefully this is something that's useful. Thanks.